Does the Fischer projection just look weird to you? Don't worry, you're not crazy. It is weird. Come along, I'll be your guide. I'll make the explanation simple and easy. Let's level up, ninjas. Hey there, ninjas. Of all of our perspective drawings for organic molecules, line angle structures, condensed formulas, chair structures, Newman projections, and Fischer projections, the Fischer projection is probably the most confusing to students and probably the least useful. There's just not a lot of good use cases for the Fischer projection in organic chemistry. But our biochemist friends do have a good use case for them. I'll show you that use case a little bit later. And Fischer projections do show up on the MCAT. So let me walk you through how the line angle structure relates to the Fischer projection, what the Fischer projection means, and how we draw it. The first thing to say about the Fischer projection is it is the least stable hydrocarbon conformation. I'm not quite sure how these projections came to be the favored ones, but the Fischer projection and the Haworth projection are all the least stable conformations of these molecules in biochemistry. That's neither here nor there, it's just another quirk of Fischer projection. If we start with this molecule with a bromine and a chlorine, we can also look at the molecular model version of that molecule. Let's follow along to see how we turn this line angle structure into a Fischer projection and what that looks like in 3 dimensions. The first thing that I said is that the Fischer projection is the least stable hydrocarbon conformation. A good way to tell the stability of a hydrocarbon is to draw its Newman projection. If we were to draw the Newman projection of this molecule, we would see that it's a staggered Newman projection with the largest groups as far apart from each other as possible. This is actually the most stable conformation for this hydrocarbon. So the drawing of the Fischer projection for this molecule must not come from this conformation. The least stable conformation would be if we rotated this back carbon such that the CH3 was perfectly eclipsed with the front CH3. So let's rotate around this central carbon-carbon bond, do a 180-degree bond rotation to bring the CH3 down into the southern hemisphere eclipsed with the front CH3. That brings both CH3 groups in the plane in the southern hemisphere. This isn't a video on how to draw Newman projections or how to do bond angle manipulations, but if you'd like a review on both of those, I have playlists for both of those topics that I'll link to in the description below. We can confirm this is the least stable conformation by drawing its Newman projection. This bond-rotated version is the least stable Newman projection because the 2 largest groups are eclipsed to each other. Here is the 3-dimensional model kit version of this molecule when it's drawn in its line angle form. And if we take this line angle structure and rotate it towards you so the bromine group is in front, we can get the Newman projection version of that molecular model kit version, which has the Newman projection with the 2 methyl groups eclipsed in the southern hemisphere. This is the least stable conformation for this molecule. The drawing of the Fischer projection will be based on this version of the molecule. If we were to take this Newman projection of the molecule and instead of looking at it from its face, we reorient our perspective and look down on it from the top, almost like we're looking at it from the North Pole, that would give us a new perspective version of this molecule. And if we imagine ourselves changing our perspective and looking down on this molecule from the top, we would see these 2 alkyl groups be pointing away from the molecule from our new perspective from the North Pole. And if we were looking down on it from the top from the North Pole, these groups up here in the northern hemisphere would be sticking up towards us. They would be closer to us as the viewer when we view it from this top perspective. Changing our model kit version would look something like this. The bond that we're sighting down in the Newman projection, the one we can't see, becomes this vertical bond when we look down on it from the top. This carbon that's in front of the Newman projection is the one at the bottom, and this carbon that's in back of the Newman projection is the one at the top. And these 2 alkyl groups stick away from you as the viewer. They're kind of behind this model kit. This is the Fischer projection. The Fischer projection is the perspective of the molecule where all of the alkyl groups are eclipsed to each other. And then we orient our perspective from looking down on the top of the molecule with that carbon chain in the vertical backbone and all of those alkyl groups pointing away from us and all the peripheral atoms pointing towards us. The way to draw the Fischer projection on flat 2-dimensional paper is we start with a series of line segments that represent the carbon-carbon bonds in the backbone of the molecule. If we add a global numbering system to our molecule, this carbon on the left becomes the one on the bottom of our chain, and the carbon on the right becomes the one on the top of our carbon chain. We then include some horizontal bonds coming out from those central carbons to show the other peripheral atoms in that molecule. And this completes the structure drawing of the Fischer projection. So if you need to turn a line angle structure into a Fischer projection, and I can't think of a good reason why you would want to do that, you would need to rotate the carbon backbone so that all of the alkyl group is completely eclipsed to each other in the southern hemisphere. Reorient your perspective so you're looking at it from the top. Start with a vertical backbone for the carbon chain of your molecule, and include horizontal bonds on those central carbons to account for the other substituents. Like Newman projections, we draw the horizontal bonds in for all of the central atoms, even if they're hydrogen. So that's what a Fischer projection is, but what does it mean? What does it represent? All of our various perspective drawings are supposed to impart some kind of three-dimensional information to the reader. So what is happening with the Fischer projection? Based on our work that we've done with the Newman projection, we can actually make a little bit of sense of this. The vertical bonds in the Newman projection are implied to be things that are pointing away from you as a viewer, like we saw when we looked at our Newman projection from the North Pole. So if we were to draw the Fischer projection in wedge and dash notation, those vertical bonds would be on dashes. They are pointing away from you as the viewer. They're sticking behind the plane of the page in the Fischer projection. Likewise, those horizontal bonds in the Fischer projection are pointing towards you as a viewer, just like they were sticking up into the northern hemisphere in our Newman projection that we were looking down on from the North Pole. So the Fischer projection in the wedge dash version might look something like this, with the vertical bonds on dashes and those horizontal bonds on wedges. Sometimes we call this the bow tie version of the Fischer projection. And that's it. That's how we can make sense of one of the oddest perspective drawings that we see in organic chemistry. Now, I mentioned earlier that Fischer projections do have a legitimate use in biochemistry. They are actually quite useful for differentiating the various sugars that tend to all look alike after a while. For example, these are all of the 4-carbon sugars that we call tetroses. If you haven't learned about sugars or carbohydrates or tetroses yet, don't worry about it, and let me just give you a preview here for when you get to biochemistry. These are all very structurally similar 4-carbon sugars. But by drawing them in the Fischer projection, we can easily see which one has the lowest chiral OH group on the left or on the right, and then we can easily see the pattern of left and right OH groups on all the chiral centers up and down the backbone. And that is how we can use Fischer projections as a legitimate tool to remember the names of the various sugars. So what are our key takeaways from this video? First, Fischer projections are just an odd perspective drawing convention. Second, when you get to biochemistry, they do have a useful purpose. Finally, what are they good for in organic chemistry? In my opinion, the only thing Fischer projections are good for in organic chemistry is turning back into line angle structures so we can do some real chemistry already. This isn't a video about how to turn the Fischer projection back into the line angle structure, but I do have that video and I'll link to it down below. Go get 'em, ninjas.
Thanks for watching. The best way you can support this channel is to let your friends know about these videos, especially ones who go to different schools. Help spread the word around the country. As always, don't forget to like and subscribe.